All right, section 2.7 is actually quite similar to a lesson that we have already done before. That lesson happened back in Unit 1. In that lesson, we were talking about adding and subtracting fractions, specifically fractions. We didn't have any variables to contend with, none of that was going on, but we were adding and subtracting things that sometimes started out with the same base or same denominator and sometimes didn't. We're going to be doing the same thing in this lesson, we're just doing it now with rational expressions. Variables are involved instead of just numbers. So last time, we actually looked at simplifying rational expressions, including multiplication and division. We found that all the processes that we learned for fractions with variables work the same way as fractions without variables. The same will be true today as we add and subtract. So our goal, generally speaking, is to get the denominators to match in some fashion. And we can't just sort of adjust them to be what we want. We have to actually make them equal using properties we've discussed about fractions. So here's our first example, and it talks about least common denominators. We need our denominators to match, and right now in this problem they don't, right? One of them is x plus 10, the other one is x minus 10, and you might be looking and saying, but Dr. Hands, it's just a sign difference. It's not that different. Well, unfortunately, when we're looking at addition and subtraction, and that's enough for it to be quite different. So in order to work through the problem, we need them to be the same. Our least common denominator, when they don't have any factors in common, but one, is to multiply the two values together. So our least common denominator here is x plus 10 times x minus 10. Now it's not very friendly looking in the sense that, oh, I just made it a lot bigger instead of reducing it with the other things we did in the last section, which made things smaller. But it's actually pretty nice when they have nothing in common to identify their least common denominator. You just multiply the denominators. What's harder is when they have portions of the denominator in common and not the whole denominator. So we'll encounter those here in just a moment. These, like the previous problem just said, identify the LCD, the least common denominator. These problems actually say add and subtract. So please be careful when you get to your homework that you pay attention to what the problem says to do. It would be very unfortunate to spend a whole bunch of time on this problem going through and adding or subtracting these values together when that wasn't the problem you were asked to do. You were just asked to identify the LCD. Yes, ma'am.
So would the answer be the x plus 10 and the x minus 10, or do you have to actually do something with that?
You mean multiply them back out? So this is actually a really good question, Jenna. It's not wrong if it gets multiplied back out, kind of like with Haven's questions that she was asking. The unfortunate scenario is that if you were actually adding and subtracting this and you multiply it back out, then you'd have to factor it back out at the end to make sure you don't have anything in common that can reduce. So we definitely want to leave it in factored form for our own benefit, and your answer can stay in factored form too, unless you just really want to multiply it back out.
I was also wondering, if it was only asking for the LCD.
It's only asking on this LCD written side by side, that's it. Yeah. So taking a look at number 2, we notice the denominators match. That's fabulous, because when the denominators match, we're already able to add across the problem. So we can't just extend this and add the top and add the bottom. That's what we did with multiplication. It works. It doesn't work like that with fractions. And if you'll remember, I'm pretty sure back in the day, it's been probably almost like 2 months ago, I gave you an example of something like maybe 1/4 plus, I probably did we'll do 1/5. 1/5 plus 2/5. And we talked about the fact that that was 3/5. So if you imagined a pizza, 5 is a terrible number, but pretend you had a pizza that was split into 5 pieces. Nobody's going to do that. Pretend. And I ate 1/5, and Sean ate 2/5. Then the total we would have eaten together is 3/5. Not 3/10, 3/5, right? The pizza's still, we each ate 1/5 of each of our slices. So when we're looking at these, we do not add denominators together. The denominators stay the same. They tell us how something is broken apart. It's only the numerators that get combined once the denominators match. So on this particular problem, the denominators match. So we're simply going to combine the numerators. And when we can, we're going to simplify things. So on this one, of course, we can. 8 plus 6 is 14. It is 14 over 5x. I'd look from the top to the bottom to see if there's any reducing going on. I can't. They don't have anything they both divide by, so I stop the problem there. The same thing happens on number 2. The denominators match, y minus 5. So we keep the denominator, y minus 5. And we add or subtract, whatever it is, this one's subtraction, across the numerators. So I have y minus 2. Please don't forget everything you just learned in the last section and start canceling things out. Y minus 2 is a factor on top. Y minus 5 is a factor on bottom, and they are not identical factors. You cannot cancel terms. Okay, and let me remind you again why, because somebody's going to do it anyway, even after I just told you not to. If you had 3 plus 4 over 3 plus 5, this should give you 7 over 8. If you tried to cancel them and do that this way, that would give you 4 out of 5, and 4 over 5 is not the same as 7 over 8. You cannot cancel like terms. Will not result in equal quantities. So that's good. It means I'm done right there and don't have to go any further. This one, actually the next two, 4 and 5, everything on this page, they're alike, the denominators, right? It's very exciting news because when the denominators are alike, we have less to do. So if the denominators are alike, we keep the denominator. In this case, it's 2x. We take the whole first numerator, 9x minus 3y. And then I'm supposed to subtract the x minus 10. So I need to make sure that this negative goes to each piece. So now I have negative x and I have positive 10y. Right? I'm subtracting the whole fraction. It means subtracting every piece of the numerator. And then we'll combine like pieces. I have 9x minus x, that gives me 8x. There's negative 3y and positive 10y, which gives me 7y. And it's all written over 2x. Again, I would look from the top to the bottom and ask myself, do all of the pieces have anything in common? And they don't. They're not all even. They don't all have x's, so I don't have the ability to reduce any further. And I stop. On number 5, the denominators match again, but the denominator here is far more complex than the last 3 we've done, correct? They are. So as I'm writing this out, I have z, right? Z squared minus 7z, plus 7z, plus 12. And it's addition, so I just add the two pieces together. I have z plus 3. You might be tempted by the 3 that we've done previous to this to think that you can stop. But this denominator, like we said, is far more complex. In fact, it's quadratic. It's a power of 2. It at least warrants us pausing and asking ourselves, do you think that denominator might factor, and trying to factor it? Because it could factor and reduce with the numerator. It might not, but we have to check it. So we're going to pause and we're going to check the factoring of that denominator. So it is a coefficient of 1, so I'm going to use trial and error, not trial by error, that doesn't make any sense. Z and Z. It's a positive 12, so I need the signs to match. Positive 7, so they're both positives. Two numbers that multiply to 12 add to 7. 4 and 3. And what do we notice? Yeah, there's actually something that reduces here. You may get to this point and nothing reduces, and you're like, okay, well, that felt like a waste of time. But you might have missed something that did factor if you're not careful, too. This one factored. Now, keep in mind that when it reduces like this, I'm canceling these out, every time it actually cancels to 1. Right? They didn't really disappear. We don't really use it and utilize it very often because dividing and canceling to 1 just means I multiply 1 by what's left and it doesn't change the value. But on the numerator on this one, there is still a 1 left in that numerator. So I do have 1 on top and z plus 4 on bottom. Any questions so far? Okay. Things are going to change on the last four. As you're glancing through the last four, you might notice that now we're hitting things that don't have denominators that are the same, right? So our first step is going to be creating them or making them the same. Now, they aren't that different on number 6. One of them's 3a and the other one's 3. They have the 3 in common, right? That's good news. So in order to make them exactly the same, I would need to multiply the 3 by a. But don't get to just go putting an a in a denominator that didn't have one before. Right? I'm really multiplying by a. And I need that whole fraction 2/3 to stay equivalent to what it was before. So if I multiply by the denominator by the 3 or by the a, I have to also multiply the 2 in the numerator by a. Whatever I do to the bottom, I have to do to the top. And while we didn't actually do it over here, that problem number 1, if we had actually done this problem, that's what we would have done. We would have had to multiply this denominator by x plus 10 and its corresponding numerator, and this denominator by x minus 10 and its corresponding numerator. Okay, so anything that happens to the denominator happens to the numerator. So on this one, I now have a denominator of 3a on both pieces. The first fraction has a 7 on top. That's cool. There's a subtraction sign in between. And then multiplying the 2 and the a together, I simply get 2a. Considering all the pieces, 7, 2a, and 3a, they don't all have something in common, right? There's not a coefficient they have, there's not a variable they all have, so I can't reduce anything and I'm done. Okay, so number 6 had a 3 in common to both pieces. What does number 7 have in common to both pieces of the denominators, or the two denominators? They both have an x, right? So the x's match. But the numbers, the coefficients, the 6 and the 7, they don't. Agreed? I need the denominators to have all of the pieces that are present in any of the denominators. So the first denominator does not have a 6 in it, so I'm going to include it. And if I do it to the denominator, I have to do it to the numerator. The second denominator does not have a 7 in it, so I have to multiply that denominator by 7. But that means I also have to do that to the numerator. Okay, so far so good. This is exactly what we did with numbers when we talked about adding and subtracting fractions. Exactly the same. So on the top of this one, I'm going to have negative 30. My denominator is what? 42x. I'm just taking one extra moment on this one since I adjusted both my denominators to write it out. If you wanted to merge them together at this point, you certainly could. Both my denominators should match at this point, and they do. What's my second numerator? It's just a 7, right? So my denominators match, which means I can actually now add my numerators together. So my two numerators are negative 30 and positive 7, which gives me negative, what was it?
Negative 23.
Close. Try again. Negative 30, positive 7. Maybe I didn't hear you right. Sorry, I really thought you said 43. Did you say 23?
No, I was.
I'm sorry. I didn't hear you right. I apologize, Trinity.
I was like, God, am I getting this
You have such a soft-spoken voice. Be bold and loud for me, okay? Sorry, I didn't hear you correctly. It is negative 23, you're right.
very loud?
Yes. All right. Looking at the numerator and the denominator, do they have anything in common? No. If they'd both been even, we could have actually done something here, right? We would have stood a chance on that one. But they're not. They don't, so we're done. Okay, ready for the next one? 8D and 4D. What do they have in common? A D for sure. Anything else they have in common?
4.
They actually have a 4 in common. So Cameron, can you explain what you mean by there, how you can see that?
There's just multiply 4d by 2.
Yeah, so the number 8, what's really happening is that the number 8 has a factor of 4, just like there's a factor of 4 here. And so the piece that it's not got, if you will, is the 2. If you don't notice that and you simply use 4 and 8 and you swap them, it'll be okay. You're just going to have more reducing to do at the end. All right? So my children have been working with fractions some this year already, and one of my children reduces things at the beginning really well. One of my other children doesn't do reduce very well, and then they have to reduce at the end. They both get the right answer, they just go about it in a different way. So it's really perfectly fine to do that. But Cameron's right. The minimum that I would need to do to make them work is to simply multiply the second fraction's denominator by 2. And if I do it to the denominator, I have to do it to the numerator. So, with that being my minimum step, my denominators do now actually equal 8d. The first one is 9d minus 1. On the second one, I need to distribute the 2 through. What will I get? Well, I should also take notes, right? There's a positive sign between there. What? Go ahead, Jenna.
4d minus 6.
Uh-huh. All right, taking them on the right? I think so. Now what?
You add the top ones together. I can't remember what the terms are.
The top, the numerator's terms. Yeah, so the terms in the numerator that match, the like terms. So 40 and 90 give me
13d.
13d. And the other ones,
7 or negative 7.
yep, negative 1 and negative 6 give me negative 7 over 8d. 13d, 7, and 8d. Do they have anything in common?
No.
No. I'd like to mention that if you had multiplied the first one, like if instead of doing this, you thought, okay, they don't match, I'm going to do 4 by 4 here. I'm going to do an 8 by 8 here. What will happen is at the end, you will find pieces that will reduce here. That's what will happen. You'll end up with numbers that are quite a bit larger, and you will find that every single one of them at that point will actually be divisible by 4. That's what would have happened. So it wouldn't be wrong, you just have the reducing to do on the back end instead of at the beginning. And notice of it at least at the beginning. Okay. Number 9 actually concludes our discussion today, mirroring back to where we started. It looks like, kinda, on number 9 that they have an x in common. But they don't. Does anybody know why?
What is a plus 1?
Yeah. This x plus 1 means x is not a factor. It's a term inside of the factor x plus 1. I don't need terms to match. I need factors to match. So these are two completely separate factors. So it's far more like, say, problem, I don't have one written down here. Yep, I don't have one written down before. Well, it's far more like problem number 1, actually, than any of the other ones because they don't match at all. All the other ones that I've done, a portion of the factors, denominators, a portion of the denominators factor into things that have matching pieces, and this one doesn't. So since it doesn't, we simply have to multiply them by one another. So this second one gets multiplied by x over x. The first one gets multiplied by x plus 1 over x plus 1. Nothing in common factor-wise. So my denominator, I definitely want to leave, at least for the moment, in factored form. It's x and x minus 1. Plus 1. I don't care if you write the x first or the x plus 1 first. That doesn't make any difference. But they are multiplied together. And both of those denominators now match, right? This is x times x plus 1. This is x times x plus 1. They match. So we're going to clean up the numerators now. I have this x plus 1 times my 7. What will that give me? Awesome, 7x plus 7. And then over here, I have a negative 6 times x. What will that give me?
Negative 6x.
Negative 6x. Fantastic. Okay, everybody good so far? All right, so we're going to clean up that numerator if possible. What do we have? X plus 7 on top. And on bottom, I still have my x and my x plus 1. If you're hankering to multiply it out, you can. But it's actually far easier to look at and to see in this form that it's completely reduced. So it's perfectly acceptable and maybe even a little bit preferable from the standpoint of checking your accuracy to leave it in factored form like that. Okay. Any questions about that? Okay, pause for just a second.